There you go. 433.
We might have fewer people because it's voting day.
Might have fewer people because we had a project due yesterday. That's my guess. Could be voting. All right. Fourier series. We started this the other day. The relevant sections of the book basically are 9.1 and 9.2 for now. So 9.1, the three forms of the Fourier series, which we touched on the other day, but we're going to do more. We're going to do some examples. So today's goal is going to be, so you remember this when you start doing the homework, is to look at some problems very similar to problem 1 on the homework and problem 2 on the homework. Okay. The book has a lot of formulas. We're going to use their general formulas for what they call the three representations of the Fourier series. There's a lot of equations. I don't know what it is, but I think it's like 70 or some odd equations. There's too many equations in my view. It's much simpler than they make it out to be. So I'm going to try to simplify it down. All right. The 9.2 talks about the Fourier series representation of common signals. Okay. We're not going to touch that yet today. We're going to touch on that beginning on Thursday. 9.1 will be the section that's relevant to the exam. Okay. Very basic Fourier series questions. All right. So we talked last time about the idea. Let me go back, I guess, just to here. We talked about this is my introduction to this, was to say, okay, if I've got an RC circuit like this and I have cosine t as the input, one way to do this is to do differential equations. In other words, if I want to know what V out is, if the goal of this problem was, okay, I'm going to put cosine omega t as my input, what's my output voltage across that capacitor? One way to do this is to do a differential equation. All right. If I do the differential equation, I get two components to the output voltage, right? I get a transient and I get a steady state. Okay. What does the steady state solution look like if I put cosine in as my input? Cosine. All right. And it's shifted. So it's got a phi and it's scaled. It's got an amplitude that we don't know. Now, in the differential equations approach, I guess that, and then I solve for the b and the phi. So I solve for the amplitude and the phi. But if we don't care about the transient response, right, what's the other thing we can do if we don't care about the transient response? The phasor domain. And so if I go to the phasor domain, then I represent everything using what we call impedances, right? And that I'm not touching on impedance per se in this class, but you guys have seen that in 2112 or are seeing that in 2112. All right, the idea of an impedance as being the way to solve for that. Impedance and the differential equation are the same thing. There's no difference functionally between them. All right, I'm not going to get into the details of that, but that's pretty easy to see if you look at it carefully. All right. Now, impedance is nice because it means we don't have to do a differential equation and all the crap that goes along with that, right? All right, I was going to say the shit that goes along with that, which is still true, right? There's a lot that goes with it. But that's nice because it says sine waves, I said from the very beginning, very day one of this class, sine waves are really important because basically anything I've got, whether I got a radio waveform, power waveform, audio waveform, all the common stuff you deal with, usually a sine wave, right? Or possibly it's a sum of sine waves. And that's what a Fourier series is. All right, so in this case here, let's say I change that input to a square wave. Now, a square wave happens all the time in digital systems, right? What does that guy look like in a digital system? What would you call that? Not a square wave per se, but what? A clock signal, right? And the amplitude might not be 0 to 1 like I've shown it there. All right, but it would that's what a clock signal looks like. Okay. Now, can I solve for V? If this was my V in, right, the square wave here, if this was my V in, can I solve for V out using impedance? In other words, could I just No, I can't. Right? Why not? What does the impedance analysis method implicitly assume? What kind of V in do I have to have?
A smooth and continuous V in.
Well, not
like a sine wave or a cosine wave.
It has to be a sine or cosine. That's the only choice. What we call a pure tone, right? So a sine or a cosine. This guy we looked at last time, we're going to look at again. This guy is a sum of sine waves. That's the idea of a Fourier series. So technically what I could do is I could figure out what sine waves are inside of that waveform, and I can do analysis with impedance at each of those individual frequencies, which actually turns out to be a useful thing to do when we're making something called a filter. All right, you guys made a filter in the project. We didn't really talk about per se what the filter was doing. If you did it properly, what you should have heard is the signal that went in had some noise to it, and then the signal that came out had less of that noise. So conceptually, you can kind of get the idea of a filter. The way we design filters is we think about what frequencies make it through the filter. So what sine waves make it through and what sine waves don't. All right, we'll look at that later on. We got to get the basics down first. All right, this guy is clearly periodic. All right, what's our definition of a periodic waveform? It repeats
More
itself.
than that repeats over a series or over a period.
Over a period. So that means that my definition of it is that x of t equals what? X of t plus capital T, the period. Yeah. All right. So in other words, if I shift ahead in time by t, that it will be equal to each other. And more generally, I can say x of t plus nt, right? I could go 1,000 periods ahead and it would have the same thing, right? I could also go 1,000 periods behind and it would be the same value. All right. So that's our general definition of a periodic waveform. We can take that waveform. And the idea here, the definition of a Fourier series that I use functionally is to say that any periodic waveform can be expressed. This is a little bit more broad than what I referred to, that this periodic waveform can be expressed as a linear combination of periodic, what I call basis functions. Okay. It's just some semantics. I'm not going to get too in the weeds on that. All right. But it's periodic basis functions. And that sounds a little bit funky for a second, but let's think of an example of this, right? Let's say I got what you did in physics, right? So in physics, you use vectors and you said, all right, here's the XY plane, right? So if you think about it, any vector in this space can be written as a linear combination of what? When I say a linear, first of all, when I use the word linear combination, what is it that I mean when I say a linear combination of things? What does that mean?
You mean like a sum of their.
I can add them and scale them. Okay.
Yeah.
So a linear combination, like tell me, so if I have a vector in the XY plane, like I've drawn right there, I can say that any vector could be represented as ax hat plus by hat, right? You still use x hat and y hat? Okay, all right. So basically the space of all vectors, any vector can be represented as a linear combination of x hat and y hat. All right, in other words, those are the basis that form the R2 space, sometimes it's called. But basically the space of all two-dimensional vectors is a linear combination of a hat and y hat. All right, in this case, when I say that this guy can be written as a linear combination of periodic basis functions, that means that I can write this guy as a combination of some form of sine and cosine at the same frequency. So let me do it this way. Some form of sine and cosine, some form of cosine omega t plus a shift. And to stay consistent with the book, I'm going to put it as theta. Or what's our alternative way of writing cosine? The complex exponential. Now I got to be careful about this, right? So cosine omega t plus phi, that means that I could write this guy as, I'm going to say a combination of e to the j omega t and what?
Negative.
E to the negative j omega t. Those are all what I would call my periodic basis functions. And there are 3 different ways to write the Fourier series, either in terms of any one of those 3 things. And there's probably 1,000 others. that you could play around with trig to create. All right, but those are the three most common. The one upon which it is easiest to do our math is this one. All right, calculus with exponentials is easy. Calculus with sines and cosines becomes a lot harder. All right, particularly when I have to do something like f of t. You would much rather do f of t e to the st than you would f of t cosine omega t. If I do this, I have to do integration by parts, and I got to do it twice. If I do it this way, I do integration by parts, but it's a lot easier, and I only have to do it once. Okay. Now, that may not be entirely obvious to you, but one of the questions people always ask is, well, dude, you know, sine and cosine is you know, enough of a problem. Why do we have to go to e to the j omega t? It's just weirder that way. It is weirder, right? But it's also easier to deal with mathematically. And that's why we use it. If you look at any kind of signals and systems sort of thing, you typically are always doing everything in terms of e to the j omega t. It makes your math a lot more compact. All right. Again, weird, but compact. Okay. So it's a matter of kind of getting used to that. We use that terminology frequently. Okay. And honestly, I think that one's the most useful form of the series. Okay. So, and I said last time we use this in a number of different places. The example I've got here, and what I'm going to do is I'm going to turn my camera on for a second. And there I am. So the other day I did this example. Let me pull it up here again. Okay. All right. So you guys in the room won't see this as well, probably. Well, maybe you will. So if you look on the screen there, every time I talk, what I'm looking at, this guy is called a Fourier transform. All right. So it's going a level beyond what I'm talking about here. But the x-axis there is frequency. The y-axis is the amplitude of the sine wave that exists at that frequency. So what it's doing is it's actually taking my voice as a voltage signal. And that voltage is basically, it's calculating the Fourier series coefficients of my voice. All right, is effectively what's happening. Now, what do you notice about if the frequency axis is the x-axis? You see a lot of spikes popping up there. All right. As I talk louder, what happens to the amplitude of those spikes? They get bigger. All right. The louder I talk, the bigger they get. Now, what do you notice about the spacing between those frequencies there? It's fairly uniform. All right. The frequencies that come out of my voice tend to be, and not just my voice, but any voice, tend to be harmonically related. Okay. Harmonically related means they're multiples of each other. All right. We're going to talk through what that means. All right, we're also going to talk more about that Fourier transform concept a little bit further. All right, but we got to get the basics down first. So last time I introduced this idea and I said, well, where do we use this? We use this all the time. Very often what happens in the real world is I get a signal, right? I measure something, I measure a voltage, I measure a current, right? I bring that into a microcontroller or something like that. And I want to be able to know what sine waves are in that thing. Because I need to know that to potentially be able to control something or to be able to make something that I want to have happen. All right, this guy here is one common example I use, which is a good computer engineering, electrical engineering dual problem, because there's a lot of firmware that goes into this guy. So in the microcontroller, there's a lot of firmware that goes. So firmware is my term I use to refer to code that actively controls something that goes into a microcontroller. All right, so we use firmware rather than software, but this idea here, what I do is, if I have a PV panel, so a solar panel, that's a DC output, and I need to put that through a circuit called a DC to AC inverter. Basically takes the DC and turns it into AC, okay? And then I put it through a circuit that's got L's and C's, like I show right here. What this whole system does is it measures, so over here, this is the grid, right? And the grid would look like that. It would be a better looking sine wave than I drew, but it would be well, maybe it isn't. It should be a better looking sine wave than what I drew, but it may not be, okay? The goal of this whole shebang here, this whole thing, the PV panel, the DC AC inverter, the L's and C's, This system is designed to basically be a current source. All right. So in other words, it's set up so that here's the grid, right? This is VG, right? That's Duke Energy gives me VG of T. All right. This is what I do over here, everything to the left. Basically, all of that crap up there, all the DC, AC, to the PV panel, all of that, my goal is to make that turn into a current source. Okay. If this voltage here is 60 hertz, which it is, okay, what frequency do you think the current that I inject into the grid should be? 60 hertz. Should be exactly the same. Should be 60 hertz. Yeah, exactly the same. And in fact, not only should it be 60 hertz, but it should be exactly lined up in phase with the voltage. And it should have an amplitude that guarantees that I get the maximum amount of power out of that PV panel. All right, a lot of details to that. I don't want to talk through that per se, but if I want to make sure that if I have a 60 hertz grid, I get a pure 60 hertz out. Well, I gotta make sure, I gotta do some stuff looking at the individual frequencies inside of what I put out to make sure I get it right. Right. So the example I gave last time of where I would use this sort of thing, this is the voltage in epic. All right. Now it's looked at through a transformer. Its amplitude is a little bit smaller. Okay. But it really is peaking at about 170 volts. If I look, so we scaled it down to make it safer. But if you look at that, does that look like a sine wave? No, it doesn't. Turns out though, it actually has the sine wave in it, and it has what I call its harmonics. It's a periodic waveform. Let me ask you this. It doesn't look like a sine wave, but does it look periodic? Does it meet our definition of a periodic waveform? Yeah, it does, right? What was our definition of a periodic waveform? Somebody online.
X of t is equal to x of t plus.
Yeah. Yeah.
X.
Yep. So in this case, it's the voltage. So I'll say V of t equals V of t plus a period later. Okay. So this guy repeats itself every period. It looks like it does that, right? So if I look at a peak here and a peak here, it looks like they have the same values. So if he's periodic, but not purely sinusoidal, then he's a Fourier series, which means that I can represent it as a sum of sines and cosines. Okay. And so we're going to introduce some terminology here in a second. Maybe I'll jump ahead and I'll come back. I think I defined the terminology here. All right. My core definitions with the Fourier series. With a Fourier series, I have a fundamental period or frequency. All right. Fundamental period or frequency. It's the smallest. I got to be careful with this. I wrote that wrong. It's the smallest frequency of the waveform. Smallest frequency, largest period, because they're the inverse of each other. All right. It's the smallest period of the waveform and the largest period, smallest frequency. Largest period, smallest frequency. Remember, those are inverses, right? So largest period, smallest frequency. All right. We're going to look at that and then some examples, because you got questions like that in problem 1 of the homework. Okay. All right. So we have a fundamental period. And then what we have is harmonics. So the other thing we talk about is the harmonic number. Okay. So what we say is that this guy might have a frequency of, let's say it's fundamental, what we call it usually F0. Let's say that's 10 hertz. Okay. So let me ask you this. What would be the second harmonic frequency, do you think? If the fundamental is 10 hertz, 20 hertz, right? So 2F0 would be 20 hertz. That's what I call the second harmonic. Okay. Now, if I had 3F0, that would be what? The third harmonic.
Yeah, 30 hertz.
30 hertz. Okay. 30 hertz. My third harmonic. Okay. And I don't necessarily have to have all of the harmonics, right, in any given waveform. One of the things that we do is if I said to you, hey, I've got a square wave, one of the things that we need to do is to figure out what are the amplitudes of all of those at each of those harmonics. That's what we'll get to on Thursday. Okay. I want to look at some basics still here today. All right. So what, back to my example here where I said, okay, well, I've got a voltage on the grid that looks like this thing, very junky looking, right? You ask a Duke engineer and they would tell you that was very, very junky. All right. And it is, right? This is what I would call low power quality, but it happens very often in the real world. What I might do is I might want to calculate. So what you're looking at here is essentially the amplitude at the third harmonic, the fifth harmonic, the seventh harmonic, the ninth harmonic, so on and so forth. All right, and there's three different bars here. This came from a graph out of a paper that we did, where basically was saying the originally at the third harmonic I had something that was 5.3, and then I did some smart control and I made it very, very small. Okay, let's think about this for a second. If this was a 60 hertz waveform, all right, in other words, if the base fundamental frequency of this guy is 60 hertz, what's the third harmonic? N equal to 3 corresponds to what? 180. Okay, 180 hertz. And you may be asking yourself, what happened to 2, 4, 6, 8? We didn't appreciate them, right? 3, 5, 7, 9, 11. So I only have the odd ones here. Now, it just so happens this guy only has odd harmonics. Okay, he doesn't have the even harmonics. Okay, now I know that because I know how to calculate those, right? We haven't talked about how to calculate those. All right, but this is a very common thing to do. So if you look at what goes on in my microcontroller here, my microcontroller actually has a controller at each of those harmonic frequencies. So it's got to do calculations to figure out, well, what's the amplitude of the current at each of those harmonic frequencies? And it uses the techniques we'll talk about here. And then I have a control algorithm that makes sure that the amplitudes get to a desired level, which is very close to 0 for the harmonics. Okay, all right. A lot of details there, but it's useful stuff. Fourier is extremely useful for what we do. Okay, as both in electrical and computer engineering, right? This is actually, in this particular case, all the analysis is done in code and software in the microcontroller, right? So this is important for both computers and electricals. All right. Now, we talked about this last time. I said, what if I have a square wave? All right. And I said, okay, well, if you look at the square wave, the fundamental period of this guy, first of all, if I look at it, the period here is t. It's very obvious. What's the fundamental period of this guy? T. All right. He repeats at t. Now, it's not always going to be as obvious as this guy. This guy's pretty obvious. I can just look at it and say, well, the period is t. That's the fundamental. Okay. Now, clearly, what I showed last time is I can fit a sine wave into that. Okay. And so what I did is I said, well, I'm going to put a sine wave into that thing. And I know that the amplitude of that sine wave to fit in properly should be 4 over pi. Now, how did I know that? Because I know the math, right? All right. You guys need to learn the math. That's coming later. All right. Now notice that the frequency here I write as 2 pi because the period was 1 second, right? So the angular frequency should be 2 pi radians per second. And if I just put sine in there, right, there's sine and there's my square wave that I drew. Well, I said last time, if I really want that sine wave to fit into that square wave, what do I also have to do? Right? It doesn't fit nicely just yet. If I want to fit it in super snug, do what?
Shift it up.
Shift it up, and I added 1, right? If I added 1, then I got to this, okay? Now, what I started talking about last time is I said, well, I can also begin to put in other harmonics. So I put in the third, all right? When I put the third in, he looks actually even a little bit closer. I put in the fifth, he looks closer still. And in this particular case, I went all the way up to 99. Now, he grew some ears there, all right? But it's definitely closer, all right? And in theory, I have to add in infinitely many harmonics to actually get up to the sine wave, or to the square wave, all right? In theory, that's true. In practice, it's not really true, all right? But in theory, that's true.
Are we going to learn how to figure out those constants B1 through B whatever?
Yeah, you are. That's what we're gonna do more of that really beginning on Thursday. Today, what we're gonna do is we're gonna look at this and we're gonna say, well, what if I'm given the sine waves and I have to figure, by looking at them, you have to figure out what the amplitudes are. All right, so we'll talk more about how I do the calculations for a more complex waveform. So back to what I said at the very beginning. So today and what we did last time, we're just going to talk about just sums of cosines and sines. For a general waveform like a square wave, we'll talk about how to approach that from a general perspective beginning Thursday. The homework that you've got really focuses on this 9.1, which is really to get us, I think it's important to just understand the basic concept, and that's what 9.1 focuses on. Okay. All right. So so the way, I guess, to end that up there basically is what that says is if I had a square wave voltage source, I could basically represent that character like what I've shown here. A square wave voltage source is equivalent to basically a sum of a bunch of cosine and sine voltage sources. Okay, that's a way of thinking about this that often makes it a lot easier to do analysis. Okay. Now, what I said earlier on is I said, well, a Fourier series, the idea is I can take any periodic waveform and I can represent it as a linear combination of periodic basis functions. And I defined for myself 3 sets of these basis functions, one being cosine and sine, one being cosine with a shift, and the other one being the Euler identity. Okay. And the one I said was the easiest was the complex form of the series. There's 3 forms of it. Math, they typically show you this one here. All right, but it really is from an engineering perspective, from an analysis perspective, that this one becomes a lot easier. All right, the complex form of the series. All right, now we're gonna deal with this because there's some things here that you're not gonna like. For instance, this guy right here, A0/2, all right, and C0/2. I know you're not gonna like that. We're gonna talk a little bit about that because that's what's gonna cause you to lose some, to bang your head into the keyboard while you're doing your homework. Is that over 2? Okay, we can get to that. All right, these things are all equivalent to each other. And all right, so I talked about this idea previously. All right, but what I want to do is I want to continue just unpacking the concept because I think you should have all seen the sum, the big sigma notation, which is the sum, right? So what this says is the sum from n equals 1 to infinity. All right, has anybody not seen that before? What's that? Should see it in Calc 2. We probably don't do a whole lot with it, is my guess. You see it, but probably. All right, well, that's good. What this means is I'm summing sine waves. I like to think of this guy visually, okay? And so basically what it says is it's in my brain, the summation is basically a little summing block like this. So what it says is I'm going to take some amount of a constant, multiply it by some number, and add that to all of the sines and cosines that go into this thing. Okay. So in my mind, what it is these numbers here, an and bn, those are what I call my Fourier series coefficients. All right. There's a coefficient that multiplies each of the harmonic terms. Okay. So we call those our Fourier series coefficients. And so notice n equal to 1 here corresponds to my fundamental frequency. What does n equal to 0 correspond to? What frequency is that? If you look at this guy, I'm adding a constant for n equal to 0. So it's the average term, right? The average term, which is sometimes what we call the DC term. Right? If you think about it, when you did DC circuits, what was true about all the sources that you had when you did DC circuits? Well, they were constant, right? All of your sources were constant. If I have a constant, what's the frequency of a constant? So in other words, if I looked at, let's say, 5 volts over time, what's the frequency of that guy? How quickly does it vary? It doesn't vary. So its frequency is 0. All right. Its frequency is 0. So I can think of DC. In other words, if I had 5 volts, I could think of that as 5 cosine of 0t, right? That's a perfectly fine way to think of it, right? It's got 0 frequency, right? 5 cosine 0t is 5, right? It doesn't move at all, okay? Now, what this says down here is it says, all right, well, if I'm given a waveform like the one that I've got here, so let's look at my square wave. Now, a couple of things. So here's the square wave that I drew, and this was me trying to fit the sine wave into it. But if you look at my square wave that I have here, this was the code that I used in MATLAB to generate that, right? So I called square just like I'd call sine, all right? And then I added 1 to it, because square by definition would go from, I think, 1 to -1 if I looked at the definition in MATLAB, all right? So I added 1 to it to shift it up, okay? So if you look at what I've done here is I've drawn out what I call my basis, all right? So what this guy is right here, so let me ask you this, and I know the amplitude is small from where you're sitting. What is this waveform right here, this one right here? What is that? What's the function for that guy? Somebody online.
It's a cosine wave.
Yeah, it's a cosine. Yep, it's cosine omega naught t. All right, so what's the guy beneath him? I guess yeah, sine. I guess I wrote the S there. Gives it away. All right. Oops. Sine omega naught t. What have I drawn beneath that?
It's another cosine, isn't it?
Another cosine, but it doesn't quite look like the cosine above it.
No, it's
Cosine
got
2 omega t.
Cosine what?
The cosine we had cosine 2 omega t.
Cosine
or-
2 omega t. He has twice the frequency, right? How can you tell he has twice the frequency?
because in the time it takes this one to go through one full period, this one goes through 2.
That's right. Right. So if you look at the top one there, as he goes through 1 period, the guy beneath him goes through 2. So he's got twice the frequency. All right. He varies twice as fast as the other guy. What's the one beneath that?
Sine 2 omega t.
Yep, sine 2 omega t. And I guess I'm calling it omega naught. So often we call our fundamental frequency omega sub 0, which is maybe confusing because it's the first harmonic, but we usually write the sub 0 on it. Okay. What's the guy beneath sine 2 omega naught t? What's that?
Cosine 3 omega t.
Yep, cosine 3 omega t. And the way you can tell that is because of what?
3 wave.
Three variations in the same fundamental period. All right. And then the guy beneath that is sine 3 omega naught t. So the way I think about this is this equation down here, if it's intimidating to you, basically don't let it intimidate you. Think about it visually like this in your mind, which is to say what I have is these A0, let's skip over the A0 over 2 for now. Let's go to A1, B1, A2, B2, A3, B3, and there's a A4, B4, and an A5, B5, and there's all of that stuff. In my mind, what those are knobs basically that say, well, if I want to make a square wave, how much cosine do I need? Let's turn the knob up a little bit, right? How much sine do I need? How much cosine 2 omega naught t do I need? How much sine 2 omega naught t do I need? Right? So from what we determined previously, let's look at this. I determined that I needed, how much cosine did it take to create the square wave? What waveform did I add in to create the square wave? It wasn't cosine, was it? So let's go back, right? This was, what am I overlaying on top of that square wave? Is it cosine or sine? It's a sine wave, right? No cosine, right? So basically what that's saying is this guy is equal to 0. Take the cosine and multiply it by 0. Don't need that, okay? I do need some sine, all right? So it turned out I needed 4 over pi. Again, we haven't talked about how to make that. I didn't use any of the even harmonics to do that, did I? So what would A2 be? 0. And B2 would be 0. All right, they're both 0. Now, again, I don't want to get too far removed here, but I was using 4 over 3 pi for this guy. All right. Now, let me ask this. I needed to add 1 to this thing to make it work. Okay. I needed to add 1 to this. Okay. In other words, so I needed to make this guy equal to 1. This is what's going to fry your noodle later, right? What's that mean that A0 is equal to? 2. Right? We'll give some meaning to that later. It's a little bit weird. All right. But what I can see is that in my head, these things are basically, this equation basically refers to the fact that I need to know what these sort of multipliers are, right? I need to know what the value of those knobs are to be able to get to the waveform. And usually the job in Fourier analysis is to figure out what are the A1, the B1, all that. So let's say I start out then with something like this. So let's get to what we mean here. So 4 plus 3 cosine 10t plus 5 sine 30t. All right, let's look at that for a moment and let's ask ourselves. How did I determine what was zeros? Because I knew the answer already. That's why. All right, I knew. So the question he asked here in the room was, how did I know that A1 was 0, A2 was 0, B2 was 0? Because I know the answer already, right? But what I showed was, in my pictures was I started out with sine, and then I added basically sine 3 times the fundamental, and then I added 5 times, and then I added all the odd harmonics. Now, how I knew that comes from the math that you have to do to figure out the A1 and the B1 and all that. Let's try to do it by inspection, because that you can do right now. That's what you really have right now going on the homework. So let's say I've got f of t equals this thing shown here, 4 plus 3 cosine 10t plus 5 sine 30t. Okay. All right. Looking at that, first question that we have to ask ourselves, we're going to do this a little bit more formally here in a minute, but what is the fundamental frequency of that thing, do you think?
Maybe 10.
10. All right. The fundamental frequency of this guy is, angular frequency is 10. Okay. 10 radians per second. Okay. So what harmonics does it have? Let's say, so if I look at this, let's talk about the harmonics, the n values that are here. All right. Which harmonics are present? So the first one is present, right? What else is present here? The third, right? Because I have, if you look at the frequencies, it looks like I've got 10 and 30. So I've got the fundamental and 3 times it. Got one other frequency that's here too, right? What other frequency is here?
Is it 0 because there's no cosine on the 4?
Yep. I've got a constant, I got a DC term, we call that, right? A constant term, that's a DC term. Now, looking at this picture, I can begin to identify what those terms are here, okay? So here's my cosine. This guy would be cosine 10t. This guy would be sine 10t. This guy would be cosine what? 20t. What's this guy beneath it? Sine 20t. And then I would have, what's he? Cosine what? 30t.
30t.
Yep. And then this would make this sine of 30t. And Captain boring up here is 1. All right, it's just constant. Okay. So let's start. What do I have to multiply 1 by to get to 4? 4. All right, that's an easy question. All right, I got that. What's A0 equal to then? A0 is equal to 8. All right. Okay, what do I have next? What about A1? What's that going to be? How much cosine 10t do I need?
3.
3. What about B1? 0. I don't need any sine to make that waveform. What about A2? 0. I don't need any cosine 20t. Do I need any sine 20t? No.
Nope.
All right. I do need A3, right? Do I need A3? No, because I don't have any cosine at the third harmonic, but I do have sine at the third harmonic, right? So that guy becomes 5. All right, so now what I've done is I've determined my Fourier series coefficients for this guy. All right, I figured them all out. Now, what I say in my mind here, we're going to look at an example a little bit more like what I have on the homework for you. All right, which is to say, this is directly out of the book, this particular example, right? It's pretty similar to the ones that you have in the homework. And let me put that back here. Okay. All right. So this is right out of the book. All right. So what I have here is S of t is 10 plus 50 cosine 2 pi 1000, blah, blah, blah. All right. There's basically, anytime I want to figure out these series, I have, what I want to do for this particular problem, just to go back for a second, is I want to figure out the AN coefficients, the BN so these guys, CN, theta n, and alpha n. I want to figure out all 3 of those. All right, and that's what we're going to do in the time we've got left here. All right, so I want to do it for this guy. What's our first step, do you think? What's the first thing I got to do? Find the fundamental frequency. All right, that's the first thing I got to do. I got to find the fundamental frequency. What is that here? Well, this is tricky. So there's my equation there. 2 pi 1000, 2 pi 1750, and 2 pi 1500. Well, so from that equation, do they look like they're harmonic? Do they look like they're multiples of each other? All right, somebody got the answer already. It's 250 is the fundamental. Now that's not obvious from looking. So the first one I gave you there, right, on the previous slide, right? This guy was obvious that it was 10, right? In this case, not so much. All right, now Alex, what you tried to do right there is you tried to look at the period of this thing. And so where would I look at to figure out? So one way to do this is to look at this and see if I can see what the period is. So what's our definition of a period? Span of time over which it repeats. So in other words, x of t equals x of t plus cap t, like that. All right. Where is that here? If I look at this graph, where could I see that? Where can I see the repeating happening?
When it hits 80.
Yeah, so you went exactly where I was hoping, right where he hits 80 right here. And then if I skip all the way ahead to here, that would be a period. I can see now. I could get it at different points, right? Wherever he's right here, I could skip ahead to here, right? That's fine too. But it's usually easiest to do at the peaks, right? So when I look at this, I can say, well, there's one period right there between those, whatever time it takes to span from one peak to the next peak that it repeats. Now in MATLAB, I did that here. So here's me plotting that same function in MATLAB, where I can see between 80.04 to 80.04. You can see that there. The time here is, this is at a negative time, so negative 0.005004 and negative 0.001004. How much time is there between those 2 points, does it look like? So I have negative 0.005004 and negative 0.001004. How much time is between those? What's the delta between those two? 4 milliseconds. 1 over 4 milliseconds, right? 1 over 4 milliseconds is, if you do the math, 250 hertz, all right? 200. So 1 over 0.004 is 250 hertz. That's what Philip said when he looked at this. What Philip did was the other way that you can look at this. All right, here's a MATLAB command, a GCD. All right, what is GCD? Greatest common divisor. Greatest common divisor. So going back to your, I don't know, 6th grade, 5th grade math, when you did that stuff and you said, well, I don't need this stuff. And you usually you don't, right? Greatest common divisor, there's always least common multiple, greatest common divisor, greatest common factor, all that sort of stuff. Greatest common divisor. All right, command you want to use in MATLAB to do that is GCD. What did I do? Yeah, so GCD is set up, unless there's, and someone may be smarter than me about this, but GCD is set up to tell you the greatest common divisor between two numbers, right? So not 3 numbers, 2 numbers. Maybe it can do it with 3 numbers, I don't know. But what I did was I had it tell me the greatest common divisor of, because I know that it's set up for 2 numbers, I had it tell me the greatest common divisor of these 2, and then I took that with this. So I nested it like that. Okay.
Do we
So-
ignore the 2 pi because they all have it, or is it just not relevant in this?
Well,
calculation?
that's a good question, right? So I am currently looking at the frequency F in hertz, right? So that tells me that the fundamental frequency in hertz is 250. If I talked about the frequency omega naught, that would be 2 pi 250. Good question, all right? Usually engineers don't think in terms of radians per second. Never do they think in terms of radians per second. If you go to Duke and you say, well, I have a 377 radian per second voltage in my outlet, they won't hire you, all right? You have a 60 hertz voltage, right? So when I look at it this way, that's why I usually see it written as 2 pi f, right? Because that's really the way we typically write that, okay? All right. So good question. I did it in terms of the F values. This tells me my F naught is 250, all right? And my omega naught would be 2 pi 250, okay? And I usually don't care what that number, I just say 2 pi times that, okay? Questions up to there? All right. All right. So given that, now the next question is, what harmonics do I have? So if you look at the way I wrote the homework, in the homework, what I said was, well, all right, so what's the highest harmonic number that appears in this thing? And I called that in the homework capital N. And I ask you to identify that in the homework, okay? What is the highest harmonic that I have? So let's actually do it this way. Let's just do N. Let's do the harmonic numbers that appear in this guy, and then let's do the frequencies that they are, all right? So let's do this. So N equal to 0, what frequency is that? 0. N equal to 1, what frequency is that? 250. All right, now this gets easy. For N equal to 2, what's the second harmonic frequency? 500. Okay. And then for 3, it would be 750. And then for 4, it would be 1,000. Okay. And for 5, it would be 1,250. 6 would be what? 1,500. 7 would be 1,750. So what's the highest harmonic that appears in this thing? 7. Okay. The highest harmonic that I have here is 7. Okay. So we've figured that out pretty quickly in looking at this. Okay. All right. So that's pretty straightforward. Now let's say I want to use, I want to determine the coefficients, right? So if we remember, the one form of the series was A0 over 2 plus sigma n equal to 1 to infinity of an cosine n omega naught t plus bn sine n omega naught t, like that. Okay? That was my basic form of the series. So let's do this. Here's the AN and here's the BN. Let's go through those real quick. All right, what do I have? So let's start with, I'm going to start with n equal to 1, then we'll come back. All right, for n equal to 1, how much 250 hertz is here? 0. And I don't have either a sine or a cosine. All right, do I have any 500 hertz in this? So the thing to do is not to look at the graph, but to look at that. Do I have any 500 hertz? No. Do I have any 750?
No.
No. Do I have any 1,000?
50.
Yeah, and which one do I have? Do I have an A or a B?
A.
Yep, I got A. Okay. Now let's do 1250 there. How much 1250 do I have?
0.
0. How much 1500 do I have?
1 and sine. B.
Okay, so I don't have any cosine,
So 0.
but I do have sine. Okay. And then help me out there. So 1750 I've got as well. What do I have for it? Do I have any cosine?
0.
0. And I have,
20.
looks like I got 20 there. Okay. All right. So what I've done there is I've said, okay, well those are the Fourier series coefficients that apply to this guy. I can do this by inspection. All right. I can do this by inspection pretty easily. Okay. So if that's the case, what I ask you to do in the homework is to enter them in MATLAB as row vectors. Okay. So notice what I have here. So the way that I've done this is I've done this for n equal to, so if I wrote an n vector over top of this, so I tried to line these numbers up here for a second. So here's 0, 1, 2, 3, 4, 5, 6, 7, right? So this, everything, so 20 and 0, 0 and 0, 0 and 0, 0 and 0, 50 and 0, 0 and 0, 0 and 2, 0 and 7, right? They line up with each other. So if you look at what I've done here, okay, I've said that for the first harmonic, I had nothing. So you look at what I wrote here, I have nothing and nothing. Now I have something in the first entry, right? I skipped over n equal to 0. For n equal to 0, how much of that do I have? How much n equal to 0 term do I have? So 10. So that means my a sub n is 20, 2 times that. Now again, that's a little bit awkward, and I don't like that much myself, but Fourier defined it, not me. Okay, and to be honest with you, some smarty pants tried to define it after Fourier did. Probably he just had a constant. All right, we'll talk about why there's an over 2 in that series, but there is. Right? Just take it for granted at the moment. We'll come back to why that.
I had big part of 9/11.
Which part?
Not being around, always on vacation, never in the office.
Why do you think Barack
There you go.
Obama was in the Oval Office on 9/11?
Guys,
What is
That I
happening?
don't know.
hey, somebody's watching news there.
Nice.
Okay. We won't get into the conspiracy theories.
Yeah, that's my bad. Sorry.
Sorry. So we'll go to the MATLAB question here. So if you look at what I did here, so basically what I did was my terms go from n equal to 0 up to capital N. So if you look at the way that I wrote this, is I said in the homework, do your entries for n equal to 0 in steps of 1 up to the maximum number of harmonics that you have. Because it's the 7th harmonic and it really should be 20. It should be it should be 20. All right, just pretend it was a 20, not a 7. It's a good question. And now it doesn't want me to erase anything here. I don't know what I did to make that unerasable. All right, but that's a 20, not a 7. Okay. All right, I'll update that when I post the slides. Now, what we can do is to convert between the forms of the series. I talked about this last time. You go into the last lecture, I talk about how you get between the different forms of the series. I basically said there's 4 ways to think about a sine or a cosine at any given frequency. I can think of it. In other words, I can take some amount of cosine plus some amount of sine and say that that is equal to what I call a shifted cosine. In other words, I got a little bit of phase shift that happens in there. And I basically proved last time that if for these things to all be equal to each other, this coefficient A is C times cosine of theta, and this coefficient B is minus C times sine of theta. Now, by Euler's identity, right, what I would find is sort of the same thing here. All right, basically what I say is this guy is some amount of e to the j omega t and some amount of e to the minus j omega t. All right. So what I see from that is that my alpha terms have a magnitude of c over 2 and an angle of theta for the positive end and an angle of negative theta for the negative end. It's actually pretty easy to prove that. And then I can also prove that the A and B coefficients here relate to the C by that square root formula and by this formula. All right, that's how the angle comes in. So the way that I do this is I look at this and I say, well, if I have the Fourier series in, let's say, the sine and cosine form, I can use a trig identity to get over to this shifted cosine. And then from that, I can easily get from that form by Euler's identity over to the complex form of the series. All right, so we're gonna look at that quickly here. So let's go back. Notice what I did for C of n. Okay, that's for that. It's for this form of the series here. Okay, where what I called it the shifted cosine version. What I did was I basically took this definition that I had here, right? C equals square root of a squared plus b squared. I've already gone through and I figured out the a's and the b's, right? That's what I did previously. We figured out the a's and the b's, okay? To get C, notice what I did. I did square root of a squared plus b squared, but notice I have this dot square. What do you think the dot square does? So if I want to square something, I use that caret symbol. Okay, and that's squaring it, raising it to the power 2. Why do you think the dot? So it's element wise, right? Which means that I want to apply the squaring to every element in A, and add the result to every element in B, after it's been squared. So an squared is going to create a vector the same size as an. Bn dot squared is going to create a vector the same size as b sub n. Adding them together is going to create a vector that's the same size. And taking the square root is going to take the square root of every entry. All right, now I could have basically manually calculated all of the C sub n values from all the A. I could have done that. Could have done a for loop, right? All sorts of things you could have done. But this is one way to do it all at once. Okay. Now, let's think about how I would do this, the alpha, that complex version. All right, we're gonna do this quickly. All right, let's look at this guy here. All right, so this guy right here, 50 cosine 2 pi 1000 t. How am I gonna get that into the complex form of the series? Well, I need Euler's identity, right? So what's Euler's identity for this guy? 50 cosine 2 pi 1000 t.
50 over 2.
Yep, 50 over 2, so 25. E to the j 2 pi 1000
t, and then plus e.
50 over 2
e to the
negative j 2 pi 1000 t. All right. So we said 1000 was which harmonic here? The fourth. Yeah, the fourth harmonic. So I would call this guy right here 50 over 2 alpha 4. What would this guy be? Alpha minus 4. Okay, alpha minus 4. Now I may have to post the video to kind of guide you guys through this a little bit more, but notice my alpha vector is huge. All right, you can see why my alpha vector's got to be huge, because it's going to have twice as many points as the A vectors and the B vectors, because it has negative frequencies. So if you notice what I've done here, there's my 50/2 and 50/2. It appears twice. All right. The guy in the middle is n equal to 0. All right. So I'll post a video that goes through that. All right, in some more detail to let you guys sort of see that. But I think the basic thing should be sort of understood from this, right? So if you can look at this and you can see this in the AN BN form, then I can just use Euler's identity to transfer it over to the alpha version of the series, the complex version of the series. And then what I can do is, using these equations here, basically using the trig identity, if I know this form of the series, I can figure out what C and theta are, right? So that is basically the process, right? So I'll post a more complete example of this, all right? And we'll probably finish this one up at the beginning of class next time. But I think that's enough for you guys to be able to get started on the homework, all right? The first problem gets through looking at identifying the frequency, all right? And the next part, the second problem, deals with identifying these coefficients. All right, so I'm going to stop there.